Okay, so this problem is it's conservation of mechanical energy. Now, what I have written here, the idea with conservation of mechanical energy, mechanical energy initial plus or minus any work done by a non-conservative force will equal mechanical energy final. Now let's talk about the work non-conservative. In this problem, do we have any force doing work other than gravity or spring? No. What's the only force that does work in this problem? Gravity. The only force doing work is gravity, because that's what pushes the kid down the hill. They tell us that the hill is frictionless. If friction were present, then would we have a non-conservative force? Yeah, if friction were present, then mechanical energy initial, and mechanical energy final would not be the same. So then we'd have to account for it by factoring in the work done by friction. Does that make sense? So for this problem, what's the work non-conservative? The work non-conservative is what? 0, because the only thing doing work is gravity. And gravity is conservative. All right, so what we have is the mechanical energy initial is going to equal the mechanical energy final. What do I mean by mechanical energy? Mechanical energy is kinetic energy, potential of gravity, and potential of spring. Okay. Now, whenever you do potential of gravity, you have to set a 0 point, and the best place to put your 0 point is at the lowest point in the problem. So this kid is going to go, woo! He goes down the hill like this, and then what we're looking for the velocity at the lowest point, at the bottom of the hill. Oh no, I'm sorry. We have the velocity. The velocity down here is 3 meters per second. That's V final. V initial at the top is 0, right? The problem says that he starts from rest, and then what we're looking for is the height of the hill. And the problem says no friction, okay? All right, so whenever you deal with potential of gravity, you have to set your 0 point. Where's the lowest point in the problem? The bottom of the hill. So put the 0 point down here. And this diagram already did that. See right here? Where did they measure H from? From the bottom. So the 0 point's at the bottom. All right, so we're solving for H. So mechanical initial equals mechanical final. So what you do is you expand this. You go, okay, kinetic initial plus potential of gravity initial plus potential of spring initial is going to equal kinetic final plus potential of gravity final plus potential of spring final. Does this problem have any springs in it? Nope, so we can cross out the spring. No spring energy. Cross the spring energy out. All right, what else goes to 0? At the top of the hill, what's the kid's velocity? 0. So what's the kinetic initial? 0. What else is 0? So the kid goes down the hill, slide, slide, slide. When he reaches the 0 point at the bottom, what's the potential of gravity final? 0. So what we're left with is, potential of gravity initial, right? That's his starting energy. The only energy he starts with at the top is potential of gravity. That potential of gravity is going to be equal to kinetic final. Basically what's happening is the energy he starts with at the top of the hill in the form of potential, it gets converted to kinetic. It's like the same thing when I take this pencil. What type of energy does this pencil have? Potential. I let it go. The potential turns to kinetic. Okay, so now what we do is we plug in the equation. Potential energy is mgh. The kinetic energy is 1/2 mv squared, where that's v final. Now check it out. Notice they give us the mass. Did we actually need that mass? This could have been a little kid or a big kid or a somewhere in between kid. Doesn't matter, because look at what happens to mass here. The mass cancels. Doesn't even matter. So his wait, we're solving for h. I keep doing velocity. H is going to be equal to VF squared over 2G. All right, so this will be 3 meter per second squared over 2 times 9.8. So that's going to be the height of the hill was 0.46. H comes out as 0.46 meters.
Isn't that kind of a lame slope?
Yeah, the hill is like, as high as my knee. Right, that's about half a meter. Yeah, that's not a very big hill. That's lame.